Okay, thank you for the transition. Yes, today I am coming to speak you about something that has been that has made Paul Tapponnier very famous, and to say the extrusion model. And I have been part of this history, but I will try to give an historical perspective to that debate today. So, extrusion tectonics, where do we stand 40 years later? Okay, it all started, as we have seen since this morning, from the work of Tapponnier in MIT when he discovered the Landsat images. And he liked to say the story that he took the image and put them in the floor and progressively make a mosaic, and then realized that first he was seeing faults, big faults, and then these faults were very long and very big. And from this Landsat imagery and from also some earthquake, this is... He made that very famous map of the active faults in Asia. And then from the work he had done in École des Mines, where he learned about soil mechanics, he applied the slip line theory to this collision. And here we have the example of the eastern side of the collision, where this makes a corner. We have the indenter here and makes very special lines that are potential strike slip direction. The blue are the left lateral and the red are the right lateral. And it seems to work very well with the active faults. But Tapponnier was not only a geophysicist, he was also a geologist. And he saw that, in fact, the Red River fault that is here is, in fact, a main boundary in the geology of Indochina and South China. And then he wanted to understand what was going on at a larger time scale, going back, further back in the past. And he also saw on the map, this old geological map, that there are here metamorphic rocks, very narrow and very long range. Then he went in the field. Okay, that's a big word, because in fact he told me that he could stop only one time, one stop along that zone, and he saw that there were nearly vertical foliation, horizontal lineation, shear criteria that was not very used by many people at that time, but he knew that, and that this observation at one stop told him that maybe there, these metamorphic rocks says it was maybe a left lateral shear zone. And then another time he went to Vietnam and looking at pebbles, quaternary pebbles, saw that the direction of shortening in the pebbles is north-south contraction, which is in fact compatible with right lateral shear on the Red River. So there the Red River could be right lateral. At the same time, with Gilles Pelzer, we have to start like this, yes. He did this very famous experiment. This is not the original one, but the one he did later, so he could do a movie. And where with this rigid indenter, this free boundary here, this plastic media here, he observed the deformation of Asia and the formation of two big blocks with two large faults. Note that he never said that this is rigid, and it is not rigid. There is a lot of deformation here, even within the blocks. And so putting this is then interpreted that this could be the Red River fault, this could be the Altintag fault with the two main blocks, and made this very famous model of two stages extrusion, with the first stages where we have Sundaland, or Indochina, as we call it in French, that was extruded to the south, east, along the Red River, that was left lateral at that time, and then in the second time, extrusion of South China and Tibet towards the east, along the left lateral Altintag fault, with the Red River fault being right lateral at that time. So there we find the left lateral and the right lateral. At that time, there was other model, other people proposing how Asia could deform, and we look in this southeast part of Asia. And there was, for example, this model that assume a Newtonian rheology for Asia. And of course, when you do that, even if you have a free boundary on that side, you don't have any fault. Another model proposed by Dewey. I'm sorry, I lost the 14 reason why extrusion was wrong. Then proposed that there was in fact a big right lateral shear zone with India going north, makes a right lateral shear zone with Pacific. And then here you will have bookshelf faulting, then you will have short, small offset left lateral faults, all the same amount of offset, and also never reversal of the shear sense. And then another model we have seen a few minutes ago, where this is an experiment, an indentation experiment, but in that case, you will also have a broad right lateral deformation zone, but in that zone, you don't have any other strike slip fault, and you just have normal faults. So what is key here is to understand what is going on here along the Red River. So it's why Paul look again at these maps and target this zone to go. And this was at the beginning, it was my PhD. And we went several times in the field, including with Paul over the years. And the questions were, at this time, was there a very long left lateral fault? Yes or no? When was it active? How much offset on that fault? And did the fault later reverse to right lateral? I will be very short on that part, and I will start by this. In fact, there is a fault there that is a very important discontinuity in the morphology of Southeast Asia that you see here. And in fact, maybe you see also that the rivers are deflected in a right lateral sense. And this was already a work from Allen and al. And this was later the PhD of Van Replumar. And here you have, for example, a view of the fault, of the morphology of the fault in the field that is running here. In fact, you have two different faults, one here and one another here. The conclusion of that work is that, yes, there is a recent fault, and that fault has been active as a right lateral with a total offset of about 25 kilometers. Now, what about the deep rocks, the gneiss? The outcrop in 4 different ranges. That's Dainui Convoy, Ailaoshan, that is nearly 700 kilometers long, Diansanshan and Shuilongshan. Altogether, it's more than 1,000 kilometers long from Tibet to the shore of the South China Sea, with lots of outcrops here very close to the sea. For French people, this will be like if you have a fault crossing all France from Dunkerque to Nice. What do you see there? You see, in fact, these rocks are not only metamorphic rocks, but they are very deformed. They are what we call myelonite, and they show a foliation. That foliation is sometimes, most of the time, quite vertical. Here below, beside Paul Tapponnier and Mark Harrison, and here it's spectacular in the Diansanshan. In some places, the foliation is less steep, but in many places, the foliation is very steep. And on that foliation, you have an horizontal stretching lineation, here with Robin and Tapponnier looking at the very famous Dali marbles. In Chinese, Dali stone from Dali means marble. Okay, so it's very famous stone. And in fact, it's very deformed within that shear zone, with also here you see the horizontal lineation. And here, everywhere along the 1,000 kilometer long shear zone, the lineation are parallel to the belt. So what do you do when you hired Robin Lacassin to come to explain you what is the shear criteria and so on? Then you look to the shear criteria, and you see that everywhere the shear criteria are left lateral. So at this point, what was the Red River fault? We change a little bit. We say it's not a fault, it's a shear zone, and we name it Ailaoshan, from the longest of the range, Red River shear zone. And it's left lateral. We proposed some offset along that fault with various geological formation. And when we sum all these possible offsets, we propose an offset of 700 plus or minus 200 kilometers. As we said, not everybody agree with this. And here you have some kind of a list of people that just disagree. A first point I should make that since then, there are only 2 examples of right lateral shear criteria. And in fact, it's criteria I don't believe. When I say example, it's at one place, okay? And in fact, everybody agrees now that it is a left lateral shear zone. But the offset is much more discussed. Some people think that it's just impossible to see any kind of offset between the 2 sides of the fault. Other people think that there is some offset of maybe 250, 280 kilometers in the south, and maybe larger in the north. And many people discuss that there could be any link between the fault and the opening of the South China Sea. Well, no, for this, because later I will tell you when this stopped, okay? Well, the answer, it stopped 17 million years ago, so no focal mechanism. But this offset is very much discussed, but if you look for a newer publication, because now the geology is better known now, that you see that very famous upper Permian emission basalts are offset by at least 450 kilometers on the fault here, left lateral, I should say. If you look at the very complex suture zone here in that zone, other people propose that it is offset by 600 kilometers left lateral. And if you look at Eocene magmatism, very special magmatism with adachite, it's there, and it's offset by at least 500 kilometers. These rocks are around 35 million years old, as we will see soon. Sorry. So what is going within these deformed rocks, within this gneiss? These are a picture of deformation in this gneiss. What is very striking is that you have evidence of deformation, left lateral deformation, at very various temperature. And you start at very high temperature. Here you have a beautiful garnet, and it's a rolling garnet. And to do that, you need to be at very high temperature. I will not go into the detail of this. This shows also that you are at high temperature. And it's temperature that's compatible with partial melting. And then the deformation continues while the temperature is going down to temperature around 300 degrees C. Why is this important? It is because if you can date this metamorphism, then you will date the fault and the left lateral deformation. So it's what we did with Mark Harrison in UCLA, taking advantage of the very first French Cameca ion microprobe to date monazites. Some monazites directly in situ, just very tiny minerals that you can date. And we date some that are within the garnet, so that they have to be contemporaneous to the metamorphism, and some that are in the matrix. And if you make a summary of these results, here on the right, you have, in red, you have the ones that are within garnets, in yellow, the ones that are outside, and the same color code here. This is just the histograms, and this is the full period, and this is a zoom only on 60 million years. And you see in the south, in the Vietnam part, you have many different ages. So you have what we have called inherited ages, but you still have many ages that are tertiary, that are Miocene. If you go in the north, all along here, you only have these Miocene ages. And then the conclusion is that this metamorphism took place between 35 and 19 million years. And this is the duration of, this is one way to see the duration of the left lateral shearing along within that shear zone. There is something else. I told you that the temperature is compatible with partial fusion. Then you have also dikes that are in place within the shear zone. This very nice outcrop here with the G. Shaosheng coming down. This was the day of the discovery of that very famous outcrops. And you can show that you have some rocks that are partial melting during the deformation, but also you have outcrops where you see the dikes, and you see the dikes, some are very, very deformed, some are a little bit less deformed, and some are nearly not deformed, and you have sometimes some that are not deformed at all. So another way to discuss the timing of the shearing is to discuss the timing of these dikes. And these are the first results. Again, histograms with the general view here and the zoom here. You see all these dikes are between 34 and 20 million years. So this is a second way to discuss the timing of the left lateral shearing. So if you put this together, you have the dikes, you have the metamorphism, you go to left lateral shear between 32 and 19 million years. And if you take the offset, it gives you a rate on the order of 5 plus or minus 1 centimeter per year. Okay, what has been done since? Many papers have been published. Many papers discuss the age of this fusion and of these dikes. And basically, the age are the same. We have here ages around 35 million years that are outside of the shear zone, that is this volcanism, that has magmatism and volcanism that has been offset by the faults. And within the faults, these are the new histograms with much more data now. So the conclusion of this is to say that the very least deformation started at 28. In fact, more likely started around 34. And it is not at all that it started after 21, as was proposed by myself in 2006, when he was discussing work. Taking the advantage of this very nice outcrop, what we could do is to take each dike, to date each dike. Hopefully each dike, the most deformed is the oldest and the less deformed is the youngest. And from quantifying the deformation, we could quantify the strain rate at its outcrop and for a duration of about 8 million years. And we go to a strain rate of 310 to the minus 14. Well, this is nice, but it's only in one place in the shear zone, and it's very difficult to find the same kind of outcrop in other places in the shear zone. But we use this to calibrate another method that is based on the size of the quartz. So it's, you can sample quartz nearly everywhere. That method is called quartz strain rate metry. So we calibrate that method from that outcrop, and we could use it on the wool width of the shear zone. And this is what we get. This is the calibration place. And in fact, we get much higher rates on the boundary of the shear zone. So here we see the location of deformation on that boundary of the shear zone. What is funny also is that if you integrate the total deformation rate from the both sides, you get a rate of about 4 centimeters per year, which is not very far from the first rate I gave you 1 minute ago. Okay, what can we do else? I told you that deformation was continuing while temperature was dropping. We have now ways to date and to see or to quantify the cooling of the rocks. We can do petrology, where we see the PT path, and we see that the cooling of the rock here is at the same time an exhumation of the rocks. They lose pressure, and we can have ages to date this cooling. Here you have the cooling of the rock, the timing of the cooling of the rock, and you see you have two-stage cooling. And combining these two, you can get this kind of diagram where you have the pressure, temperature, deformation, time evolution of the rocks. And what is in red here, it's during the left lateral shear. What is here is during the right lateral shear. And so we are interested by this part, the red part, which I will call the first cooling part, if you like, which is cooling and exhumation. And these are all the data all along the belt. Here you're close to Tibet, here you're close to the South China Sea. And if you put all together all the age of cooling, of the first stage of cooling here, it's between 32 and 17 million years. So this is the second way to estimate the timing of the shear zone. If we look now in detail to this part, the Isle Ocean, what you can see is that the cooling doesn't take place at the same time everywhere. It's a diachronicity of cooling. It starts here in the north. It started in the south and it propagates to the north. Tapponnier proposed a conceptual model to explain that diachronism, which we have called zipper tectonics. And the idea here is that you have rotation pole of Indochina with respect to South China, but the Isle-Ocean Red River is not following that small circle. It's somehow different. And this means here you have transpiration, and in this part you have transtension. And in the middle, here, the neutral point is where you have really strike-slip deformation. What is going on? If you have rocks here, they travel here. When they reach that point, they come into the transtension part. And here, as they are in the transtension part, they start to uplift, like in the shoulder of a rift, but with mainly a strike-slip component. And then the timing at which the rock cross here is the timing at which the exhumation starts. And the rate they are crossing that point is in fact seen here by that slope. Okay, so that slope, the distance against the edge of cooling or exhumation, gives you the rate of the fault. And in that case, it gives us a timing of faulting between 27 and 70 million years and a rate of 4.8 centimeters per year. Again, a number that is very close from the previous one I told you. Now, if we look at the connection with the South China Sea, I will not say much. Anne Briet will say more about this on Thursday. And the thing is that if you take the magnetic anomaly of the South China Sea, you reconstruct the rotation pole between Borneo and South China. If you make the assumption that this is linked with Indochina, you apply this pole of rotation of Indochina with respect to South China, what do you get? You get 40 kilometers of offset at a timing that is exactly the same as the zipper and with exactly the same thing, meaning transtension here and transpression here. Okay, so this looks very clear for us. But then from 2001, approximately 2003, we could ask a question, will channel flow not flush everything away, in fact? Because many people have proposed, maybe like Laurent, as early as 2001, that in fact, the Red River is not a deep strike-slip fault, but is just an upper crystal structure, in which case this motion of that fault will not have any relationship with the opening of the South China Sea or the big picture. And also, a little bit later, a lower crustal channel flow was proposed to flow from South Tibet to Yunnan. And very lately, there was a paper in 2003 that proposed, in fact, that in the area, you had 3 episodes of deformation, 1 episode of vertical flattening, so in fact, extension, then an episode of channel flow with everything going to the northeast, and then a last event of folding of the previous structure that will make rise the present-day metamorphic range. Note that all these events, these 3 events, around 1,000 kilometers long, will have exactly the same direction of lineation, which is very unlikely. So these are not 16 points, but only 6 points where I think this is just impossible. I will just stress the 5th point here, which is that if you have a décollement, and then you fold that décollement to gain the metamorphic range, then you get the reverse, not the same shear sense on that side and on that side. They have to be opposite. And this is not what we see. What we see is left lateral and left lateral. And as a matter of fact, this was discussed already since 1995. And this is the reason why the Aleutian Red River is not a folded décollement. This is just not fitting with the field data. So now we nearly reach a conclusion. The Red River fault, Aleutian Red River fault, is a left lateral structure that was active during 34 and 17 million years. There is a link to the South China Sea, so it makes it a lithospheric fault. Red River is right lateral. We can discuss since how long exactly. And this, for me, validates the extrusion model for Sunderland. And also, what is maybe more important, that validates that large strike-slip faults are not transient feature limited to the upper crust, but they are deep-seated faults. New publication go forward with this interpretation. For example, the paper of Jiao et al. That shows that you can make a model, 3D discrete element modeling in that case, where you have both, in that case, strike-slip faults and thickening at the same time. And here it's a different model. It's a viscoelastic plastic thermomechanical model called LAMEN. And in this model, in fact, we guide Straxy fault, even if the lower crust is quite weak and these faults are going through. So yes, maybe I missed the most important. So we believe that the two-stage extrusion model stays the best way to describe Southeast Asia tectonics since the Oligocene. And now the real conclusion. This has been a lot of work for Paul during his life. And you see he's working hard to make it go through. And in fact, it was not finished. He was still working on that. We don't know yet everything, so there are still things to do. And of what Paul was doing now, you can look the poster by Monterey and Al on Friday that will show what was Paul was preparing, but it's not yet published. And well, where do we stand? I think Paul stands proudly here near the Isle-Ocean Gneisses, so I think he can still stand there. And I think it's still a very important observation. And I suggest that we should organize a special workshop on large-scale continental Straxy faults, and possibly in Delhi, a very nice place where can be some earthquake, by the way, and we could see the Yellow Ocean on site. I leave you with that. Thank you.